Hello guys, welcome to In 5 Minutes. In this presentation we are going to see the synchronous counter. In the earlier session we have already seen the asynchronous serial or ripple counter. In this session we are going to see synchronous counter. So before starting, let us say that we are going to design a mod 6 counter. For that, number of states will be 6. So there is a formula that all we know is n should be, number of states should be less than or equal to 2 raised to m, and here in this case n is 6. So if we'll put 6 should be less than 2 raised to m, then definitely the value of m will be equal to 3. Therefore we'll require 3 flip-flops in this kind of counter. So we know that there are 6 states, so let us go to the state diagram. So here is the state diagram in which there are 6 states, 0 to 5, and 0 will go to 1, 1 to 2, 2 to 3, all the way 5 will go to 0. Now you see there is a closed path, so we need to set a reset state. So let us assume that 0 is going to be our reset state. So I will point here 0 as the reset state, or whenever I will give a clear pulse, so all the flip-flops will set to 0, the output will be 0. So let us try to design this one. For designing purpose we need a table. So this is a table for synchronous counter, and we know that since there are 3 flip-flops are required, m is equal to 3, this is called as present state. Also you can call it as qn, which is nothing but the present state. Next state will be qn plus 1, and here flip-flop. Now in the exam they may ask you to design with the help of T flip-flop, D flip-flop or JK flip-flop. So here for sake of simplicity I have taken T flip-flop. Okay, so this is flip-flop input. We'll see how the input to flip-flop will give, but before that we have 3 flip-flops. So we have 3 present state, QC, QB, QA. So I have taken A, B, C flip-flops in the reverse order. All the 3 flip-flops are T flip-flop. So for the 3 flip-flops we have 8 combinations, that is anyone 0 to 7. So let me write down all the combinations. So there are total 7 combinations. Let me write down the decimal equivalent for each state. So it is 0, 1, 2. So there are 0 to 7 states. Now according to our design, what we have stated in the state diagram, that 0 state will be going to the state number 1. So this decimal equivalence, that is nothing but the state numbers. So as I am saying that 0 will go to state number 1, so present state, the column is 0. In the next state it is going to be 1. So I will write down this 1 here, 0, 0, 1. Because for the 0, present state 0, next state is 1. For present state 1, next state is 2. So I will write down the bit combinations for 2. 2 will go to 3. So I will write down here 3. 3 will go to 4. 4 will go to 5. And here is very important state, that this is state number 5. 5 will go to state number 0. So what you can see here is after 5 the flip-flop is in the cycle or in the reset state. But what about the other states which are not mentioned here? What about the state number 6 and what about the state number 7? So what we will do here, we will set it as don't care. So I don't know where the state number 6 is going, I don't know whether the state number 7 is going, so I will put this don't care. Now we need to set the inputs to the flip-flop, and what flip-flop we are using? We are using the T flip-flop. So for this input to the flip-flop we need to excite T flip-flop. So we will require an excitation table for T flip-flop. So here is the excitation table for T flip-flop, and what we see here, there is a combination of present state and next state. So here is nothing but it's Qn is the present state and Qn plus 1 is the next state. So depending upon the present state and next state combination, input to T flip-flop is decided. For writing down TC, what I will do, I will see the sections or see the column for QC in the present state and next state column for QC. So very first combination is 0, 0. So for 0, 0, TC is 0. For QC, present state, next state, 0, 0, again TC will be 0. For 0, 0, again the output will be 0. For third state, that is 0 1, so output will be 1 here. For 1 1, output is 0. For 1 0, output is 1. And 1 don't care, that is in the last two states. So I will put up here once again don't care and don't care. Since there is no combination present in the excitation table or present state next state combination between don't care, so I will simply put TC as don't care here. Similarly, you will fill up the table for TB and TA using present state and next state combination. You will fill out TB and TA. So here is the complete truth table for the synchronous counter. In the special case, we are designing the modulo 6 counter, but which is synchronous.